Professor Cha mentioned. So, but I would like to talk about the somewhat broader topic, including the result related to this topic. So, I'm going to talk about somewhat generic title, monorail films of block copolymer micelles for nanoparticle and nanopattern formation. So I'm going to show you the synthesis of silver nanoparticles and nanopattern fabrication of conducting polymers and nanopattern fabrication of magnetic materials. So that's the related to this title. And by using monorail films of block copolymer micelles. As you know, in a selective solvent of one of the blocks of block copolymers, they form micelles above the critical micellar concentration. For example, toluene is a selective solvent for the polystyrene block of polystyrene polyvinylpyridine block copolymers. So in a toluene solution, the PS-PVP form nanometer-sized micelles with PS corona in red color and the PVP core in gray color. So many research groups have demonstrated that various nanoparticles can be synthesized in the core of this micelle by incorporating a metal salt in the core of this block, copolymer micelle. Also, in addition, this micelle can be transferable onto a solid substrate by the deep coating method. Also, we recently demonstrate that this micelle or PS-PVP can be transferable onto the solid substrate by the simple spin coating method. And then we were able to fabricate the monolayer of PS-PVP micelles by the spin coating, and this film can be removed from the mica substrate by floating the film on the water, and it can be transferred onto a TM grid. And then we can analyze this film by the TM, for example, in the plan view, in this fashion. So to visualize the internal structure of this monorail film by the TM, we should stain the block, PVP block by the iodine. And then the next TM graph shows the dark spherical PVP core, and then this is the monorail film. Definitely, this is a monorail film consisting of the bright PS corona, continuous matrix, and then the dark spherical core, PVP. And we can also see that this one is a short-range hexagonal order by the Fourier transformed patterns of this boxed area. And then we further characterize the surface structure of this monorail film by AFM and then lateral force microscope. In AFM image, you can see the surface of monorail micelles, but in AFM, you don't see any specific morphology. That means the surface was covered by the same component that is polystyrene. So we can draw the schematic of a monorail film of this PS-PVP micelles, and that is PS corona outside, and then the PVP core inside. So far, the result is almost identical to the the film made by the deep coating method. So we changed the morphology of this nanopattern by simply treating with a selective solvent for the core. So simply we dipped this monorail film in a selective solvent of the core block, that is ethanol, and then the ethanol is a selective solvent for the PVP. So we see that the red PVP blocks becomes the core, and the gray color PS becomes corona. So that means that there is a core corona inversion. So to verify this kind of core corona inversion, we first stained this film as before by iodine. That means the PVP is now the matrix, So as you can see, then now we can see the continuous dark PVP matrix, that is corona now, and then we can see the white spherical PS domain. Also this short-range hexagonal order was maintained. That was confirmed by the Fourier transform of this patented this boxed area. So we will further characterize the surface by AFM and LFM as before. And then in the AFM image, you can see that the area corresponding to the polystyrene core shows the lower height. But the LFM image, you can see also the same area shows the lower frictions. That means the surface was not covered by the same component. The area corresponding to the PS core could be covered by the polystyrene. We can draw the schematic from this AFM and LFM image like this. So that means the polystyrene could be exposed to the air. We think that in a selective solvent of PVP, that is ethanol, that probably the surface could be covered by the PVP. But when the film was dried, the lower surface energy block, PS, wanted to find the air interface that could be possible. So, and then by pushing the PVP block to the side, and then they could be exposed to the air. Definitely we need more study to verify this kind of co-corona inversion and the structure before and then after the ethanol treatment. Anyway, we were able to change the co-corona. That means that we were able to induce the co-corona inversion in situ in the film. So now I want to show you how we can use this kind of co-corona inversion to synthesis of nanoparticles and fabrication of nanopatterns of conducting polymers and then nanopatterns of magnetic materials. In a toluene solution of PSPVP, a variety of metal salt can be coordinated in the PVP core. That means, for example, we can coordinate the silver acetate in the PVP core to synthesize the silver nanoparticles. Also, for the synthesis of conducting polymers, polypyrrole, we can coordinate the ferric chloride, that is a catalyst. Also, we can oxidize that ferric chloride to the iron oxide, that's a magnetic material. So, let me show you first the silver nanoparticle case. So we can, again, make the monolayer film of PSPVP micelle containing silver acetate in the core by the spin coating, as before. And then the silver acetate can be easily reduced to the silver nanoparticles by the light, even by the electron beam of TEM. So we can produce a silver nanoparticle specifically in the core block. That means the silver nanoparticle can be formed in the isolated phase. So next TEM graph shows that result. So now we have silver nanoparticles in the core block. So now we can apply the co-corona inversion to change the location of a silver nanoparticle from the isolated phase to the continuous phase. So simply, we dip the monolayer film of PSPVP micelles containing silver acetate in the selective solvent of the core, that is ethanol again. Then the PVP becomes the corona from the core, and then the silver acetate can move together with the PVP because the silver acetate is coordinated to PVP. So that means the silver acetate is now in the continuous matrix of this corona. Then we can reduce them by the light or the electron beam, and then we can produce silver nanoparticle in the continuous matrix. That means we can change the location of silver nanoparticle. That we analyze that by the TEM again. Now you can see the silver nanoparticles in the continuous matrix. That means we were able to change the silver nanoparticle in the isolated phase to the continuous phase. So now we can think, if the amount of the silver nanoparticle is above the population threshold of conductivity, we can get the completely different conductivity before after the solvent treatment. That means before treatment, the silver nanoparticles are isolated phase, we don't get the conductivity. But once it comes in the continuous phase, we can get the conductivity. But unfortunately, the amount of silver nanoparticles is far below the perforation threshold of conductivity. Thus, we decided to synthesize the conducting polymer in the domain of PVP. So, as I mentioned, the variety of metal salts can be coordinated in the PVP core. So we selected the ferric chloride that can be coordinated to the PVP block again. The ferric chloride is a very effective catalyst for the synthesis of a polypyrrole, conducting polymer. And also we can oxidize the ferric chloride to the magnetic iron oxide. So that means that we can get the iron oxide. So let me show you the conducting polymer case. So exactly the same as before. We spin-coated a monolayer film of PS-PVP micelle containing ferric chloride in the PVP core. And then we have that now the ferric chloride is in the isolate phase. Then we treated them with the ethanol to induce the core corona inversion. So now we have the ferric chloride in the continuous phase. Okay, so first we verify this one by TM again. So now we have a core containing the ferric chloride. Since we didn't use any kind of staining agent, this if the contrast comes from the ferric chloride in the core. So now we know that the ferric chloride in the isolate phase. So that we treat this one with ethanol. So we change the contrast completely differently. So that means the ferric chloride is now continuous phase. Okay, so now we are ready to synthesize the polypyrrole. So we expose this film to the pyrrole monomer to synthesize the polypyrrole in the domain of the ferric chloride exists. So we first expose this film to the pyrrole monomer, and then this is the TM result. And as you can see, now the domain becomes a worm-like structure because of the inclusion of a polypyrrole in the domain of a PVP. The contrast comes from the ferric chloride and the polypyrrole both. So, and then but if you look at carefully, this one is still in the PVP block is still the isolate phase. So, and then we treat this one with the ethanol to change the nanopattern morphology. And then this is the result TM. And as you can see now, that is a continuous phase. So now you can see expected the complete different conductivity, but unfortunately we didn't have a reproducible conductivity yet because of the film is too thin to get some reliable data yet. So, but the measurement is in progress. That means that we have at least completely different patterns, so nano patterns of conducting polymers. So making a pattern of conducting polymer is also a big issue. So we can change the morphology by simply dipping into the ethanol solution. Okay, so let's move to the today's real title. So, we can produce the iron oxide by oxidize this ferric chloride that was used catalyst for the polypyrrole synthesis. Now we can oxidize them, and then we can produce the iron oxide. That could be magnetic. So now the ferric chloride is in the isolate phase. We can use oxygen plasma to oxidize them in the iron oxide. By oxygen plasma, also the polymers could be oxidized and gone. So, and then we can remove the polymer, and then only the iron oxide now patterns. And also we can use the inverted phase, and then we can have a continuous iron oxide, and then with the nanoholes. So we characterize them by the field emission SEM, and this is iron oxide nanopatterns. So the diameter of the iron oxide is about 20 nanometer, and the interspacing is about 30 nanometer. So you can see that we produce some kind of iron oxide, and then also we use the inverted phase, and then we produce some kind of continuous iron oxide with nanoholes. With a careful look, it looks like a volcano, but I know that we need more study to verify this kind of structure. So also we try to characterize the crystalline structure of this iron oxide, and then but the contents of the iron oxide is very low to get the exact structure. But by using X-ray photoelectron spectroscopy, we deduced that this iron oxide is close to the gamma iron oxide that is magnetic. So we measure the magnetic properties of these films by using alternating gradient magnetometer, and then this with this film, this pattern, we get a typical ferromagnetic behavior. So that's good. I mean, this could be applicable for the high density storage media because it's more than 500 gigabit per inch square. So anyway, we also measure the magnetic properties of this morphology, and then our preliminary result shows a very similar result, but we think we need also more study to verify this nanopattern to the magnetic property relationship. So let me summarize my talk, and then based on the monolayer film of block-polymer micelle, so we demonstrate synthesis of silver nanoparticles and fabrication of nanopatterns of conducting polymer, or polypyrrole, and then fabrication of nanopatterns of iron oxide. Also, we were able to change the nanopatterns simply by the solvent treatment. Thank you very much.